So once again, welcome to our webinar. My name is Phil Goff and I will be your moderator today. I'm a product marketing manager and regional sales manager located near London in the UK. The initial part of the presentation will be covered by Oskar Persson, who is a specialist R&D engineer located at our R&D facility in Kalmar in the south of Sweden. And then the latter part will be covered by Magnus Melteg, who is our R&D manager located in the same facility. During today's session, we aim to give you an overview of how we are addressing our customers' needs for more and more detailed information when it comes to thermal modeling of our converters. The agenda for today's session is essentially split into three main parts, plus a Q&A section at the end. First, Oskar will explain how and why we're evolving the way our thermal derating information is presented in the product technical specifications for our highest power intermediate bus converters. Then Magnus will run a live demonstration of Flex Power Designer, focusing on the new features we have introduced pertaining to thermal analysis. Then finally, Magnus will present and explain the current FloTHERM models we can offer you, which will help you as engineers to define your system level thermal performance. Flex Power Modules is an acquisition that Flex made over 3 years ago of Ericsson Power Modules, headquartered in Sweden. As such, we've been involved in developing board-mounted DC-DC converter modules for distributed power architectures and intermediate bus architectures for more than 40 years, delivering more than 100 million modules to our global customer base. We pride ourselves in offering technology-leading solutions to our customers in the telecom and datacom markets, and now also to the industrial and railway marketplaces, and have developed several firsts in these areas where our focus is on offering the highest levels of efficiency, power density, reliability, and design flexibility, with a special focus on digital solutions. Our product range as of today covers front-end power interface modules, isolated and non-isolated DC bus converters, non-isolated point of load regulators, direct conversion products, and voltage regulator modules. Today's technologies in the areas of artificial intelligence, hyperscale computing, cloud, network security, and even 5G is pushing the envelope of required power delivery ever higher. And as such, more and more sophisticated ways are needed by our customer base to remove dissipated heat from their systems. For that reason, we're constantly asked to provide ever more detail of our product when it comes to accurate thermal derating and complex thermal modeling capabilities. We've responded to that call by implementing both new tools and extended support when it comes to thermal management, which is what we'll present today. So with that, I'll hand you over to Oskar Persson, who will introduce the first of these new tools, the 3D thermal derating information we will now provide within the technical specifications for our high-performance IBC. Oskar, over to you.
Thank you, Phil. My name is Oskar Persson, and I work as a specialist at our R&D facility in Kalmar, south of Sweden. I have been involved in the development of the quarter brick BMR 491 and the 8 brick BMR 492, which we'll use as examples in this part of the presentation. Yeah, here we go. What we see is a continuing trend towards even higher power density, more power in less space. The new BMR 491 have variants with a power density over 800 watts per square inch, one of the highest in the industry, we believe. High power density may come with a challenge. Over the years, power density of the converters has increased more rapid than efficiency. More output power per volume unit, but also more heat to dissipate away per volume unit, which put a challenge on the cooling. At the same time, cooling temperatures are increasing. Expectations on high output power, even with a 100 degrees C base plate temperatures, are not uncommon in 5G applications. To the right, we have a few pictures showing applications with advanced thermal solutions. We have a trend in that customers start moving away from direct mounted heatsink and airflow. At Flex, we have over the last years both developed products, but also methods to meet those challenges. We have also been thinking about what tools our customers might need to minimize the risk with the thermal management. The request of early information about thermal characteristics has moved us into making thermal finite element models as soon as we have a layout ready. The thermal FEM model can be compared to a mechanical model, but here we take a look at the thermal properties of all different materials in the products. We have heat sources, isolators, etc. Every component of importance is included in this simulation. We will now take a look at the design process, and then it will be easier to understand where our models origin from. This is a crowded page. But we follow a timeline from top to bottom. In the earliest phase at the top, we do research or the pre-development. In this phase, we're mainly working computer-based with simulations, trying to base decisions upon simulations. Even that the simulations often are related to specific details such as transformer design, it's also possible to make FEM on a complete converter and deliver early FloTHERM models to customers upon request. In the hardware design loop, we have moved to a state where hardware is available. The design becomes tested through its phases. Models becomes fine-tuned, design might be adjusted here and there. It's an interactive process with all the tools we have. And we measure quite a lot. So then we can find suggestions for improvements and try that out in the simulator and pick the most promising looking and implement in the next spin. When we move out from this loop, samples are ready for final testing. For thermal, a number of different verification tests will be performed. We will take a quick look at two of them in a few seconds. However, the output data is such we can publish in our technical specification with a 3-axis graph. It can be exported to Flex Power Designer, but we also calibrate our FEM model so the FloTHERM model we deliver is accurate. Let's move to the test setup. In both examples we see here, the test object is preparated with a number of thermal sensors attached to key components. Of course, the hotspot is chosen, but also important reference points for thermal modeling. The test system attached to this measures temperatures, efficiency, voltages, etc. When everything is steady state, the data is recorded, and then the test continues to the next test point. To the right, we have these traditional systems that force air from bottom to top. The wind tunnel can be used for airflows up to 4 meters per second. The downside with this type of test is that the board temperature and the base plate temperature can't easily be adjusted independent. And to the left, we have a new system using liquid. Instead of controlling air speed, it controls temperature on 2 channels, one for base plate and one for pin temperature. The reference sensors are attached to the base plate and the joint between the output pin and the test board. It's possible to program an independent base plate and pin temperature. A third regulator finds out the maximum power that can be reached without overheating the converter. The thermal blocks used is for standard desktop CPUs, and it might happen that you will find attachment for those blocks on future test boards from Flex. But let's move to looking at the output data from those systems. The traditional power derating was the one using the wind tunnel. We have 2 axes, one representing maximum power and one maximum ambient air temperature. Different line represents different airflows. This type of curves show the performance of a complete system, DC-DC converter, test board, base plate, heatsink, etc. It gives very little information how much the test board or the heatsink contribute with. It's a very nice to compare products with, but it doesn't really generate understanding of the thermal properties of the product itself. And without that, it will be almost impossible to use this as a reference for how your system will work. I would like to make a short side note about our BMR 491 and 492 family here. The product we're looking at here is rated for 1.3 kilowatt continuously. We call that power, refer that to TDP, thermal design power, and the red dotted line represents the TDP power. Above this, it's a maximum power that we refer to as a peak power capability. We state up to 1 second, which in this case is 1.85 kilowatts. And then we move over to this 3-axis derating graph. So this is the one we created with help from the new liquid-based test system with the CPU thermal blocks. 2 axes represents the working temperatures, pin temperature and base plate temperature. Pin temperature can also be referred to as a board temperature. The 3rd axis shows the maximum power the converter can deliver. And the colored sections corresponds to a power band like 1.2 to 1.4 kilowatts or whatever. Either way, you know the power level and get what temperatures you need to keep. Or you know your temperatures and the graph will tell you the maximum power. We think this type of graph is especially valuable when moving into large heatsink combinations with a load, like a CPU, GPU, or 5G amplifier stage on the same heatsink with a DC-DC, and of course liquid-cooled applications. The key with this 3-axis graph is it's something we can publish in a paper format. And now let's go to an example. Here we have a case study, an actual customer case. We had a customer that made a thermal simulation on their server application. They estimated the worst case base plate temperature to become 92 degrees and the board temperature to become 83 degrees C. And now they were a bit worried about the powering of their board. By adding a few support lines, it showed approximately 1420 watts without exceeding the maximum component temperature. So even at such challenging condition, the BMR 491 could deliver above 1.4 kilowatts of output power. And this was a straightforward question, and we think we could find a straightforward answer to it by using this 3-axis graph. And now we have come to the conclusion of this section. The new 3-axis graph presents the performance of the converter instead of the performance of a complete test system, which is the case with the traditional test setup. We think this is useful for many applications, but especially for so-called cold wall or liquid-cooled systems. We also think this 3-axis graph, despite not being an industry standard yet, serves a purpose for compare within Flex product portfolio. And it closes the gap between the traditional air-based rating graphs and a full thermal simulation. So here I would like to thank for me and hand over to Phil again.
Great, thank you, Oscar, for that explanation of why and how the thermal derating data presented in our technical specifications will change for the highest power IBCs, and one part of the 3 toolbox that we're including today. And for that, I'll now stop sharing and pass you over to Magnus Melteg. Magnus, over to you.
Thank you, Phil. I'm Magnus Melteg, and I'm an R&D manager here at Flex Power Modules in Kalmar. I am responsible for the software team and the support team, among other stuff. The software team mainly develops the Flex Power Designer, and the support team's main topic is different kinds of simulation, and they are the ones who are responsible for developing our FloTHERM models. So we will start with the Power Designer. The Power Designer is our application for configuration and simulation of our digital products. We make 2 releases of this application a year, one in the summer and one in the winter. New products are added and supported. Once they are released, they are added to this program. And since the latest release, we have a small indication here up in the right corner showing if there are new release of the Power Designer or new release of products available. So I will start the demonstration by building a new project. So what we think that you as customer know is your supplies, what you have on your left side, and the loads, what is more or less your requirement. And we will now, for example, build a very simple system here. I will create a load and I will create a supply only with our default values. And I will go up here to the project view, and here we can see. So we have the supply to the left and the load, which normally is loads probably to the right. Our mission here at Flex Power Modules is to help you as customer to fill the gap here in between. So we'll start here from the right to put a rail here. We go to the rails view. We are looking for a point of load with 12 volt in and 20 amps. Let's put 3.3, let the output voltage instead. And we will find one of our newest product here. But I will also show you a small shortcut here. If you right click on the node and create and connect point of load, the search message I just typed in will be derived from the load, and you can select here. We'll select one of our latest point of load, the BMR 469. And in the same way, we will select a IBC. I will take now as an example the 458. Pay now close attention to the efficiency view, the efficiency node here up in the configuration browser. Once I do the connection of this system, you can now see that it calculates the total efficiency of our system here, our small example system. So the reason we can do this is that every product has a power dissipation model. You can find that by clicking the rail and choosing the datasheet tab. We can now here see the power dissipation as a function of the I out, and the input parameters, the red dot here shows where we are at this moment. And this can be calculated. The result is here on the right side, 5.4 watt, and the input are here on the left side. V in, V out, and I out comes from the system we just built, and the temperature here is something that you have to come up with yourself by reading our data sheet and do an estimation. However, our recent add, if I change here the product to something that is a little bit newer, let's do the same procedure again, and I will choose this one. So connect again and back here to the datasheet view. What we can see now is that the temperature has disappeared from the input setting panel and instead end up as a result. So we now have a thermal model that based on this input can calculate the temperature that the module will have under these circumstances. So the input parameters are now instead your airflow, the surrounding temperature, your estimated temperature of the board thickness, and the copper amount in your board. So the module temperature can now be plotted on all these parameters, and we choose here to show I out, and here is where we are located for this configuration. So let's just add a load here to increase the temperature a little bit. I will make one quick here. We'll go back here to the system. I will just connect this directly to the IBC. Go back here. You can now see that we are at the top of what this module can take. And let's have a look at the air temperature based on this. Based on air temperature, we can see that we are okay still, but if the temperature increase up to 60 degrees, we will hit OTP, which is over temperature protection, which is indicated by this red part here. Can also show based on airflow. Can see here that it will be possible to decrease the airflow down to 2.5, for example. And we'll end up here, still okay. If we go back to the temperature, air temperature again, we see that we are quite close, and a warm summer will be hard for us, perhaps, a really warm summer. So the temperature that we display here is it's the hotspot of the module, and it's based on a lot of measurements made in the wind tunnel with a lot of probes, with a test board that is designed so that you can do the measurements without having to know the test board itself. So the test board is disconnected from the tests. If you are interested in more advanced simulations, we recommend that you turn over and look at FloTHERM instead, which presentation we will transfer over to right now. So I will stop sharing and back to you, Phil.
Thank you, Magnus. Let me just reshare my screen. Hopefully you see my screen now, Magnus. Could you confirm?
Yeah.
Sure. Thank you very much.
Let's continue. So our FloTHERM models are available at our website. We can take the next slide here. If you click your way to resources and downloads, you will see the view that we have here, a screenshot from to the right. And we use the FloTHERM application to create these thermal models. And our goal is to provide FloTHERM models for all new release products. It's also important that if you work with us in an early stage, it is possible for us to create a FloTHERM model based on simulated data before we even build a sample. We have done that sometimes. It's important to understand that you as customer must be familiar with FloTHERM. You need to have the application and the license. We do not do simulations for you. Instead, we provide a model that you can incorporate in your board design, in your FloTHERM model, and see how it behaves together with your design. So we have three different models at our website. SolidWorks and Parasolid are the older way we used to do thermal models on. These are more or less the necessary data you need to build your own FloTHERM model, or in that case also for other types of simulation tools other than FloTHERM. You can use this information to build your own model. However, since for a year or a little bit more than a year ago, we moved over to provide models in FloTHERM directly, because we've seen that this is what is the most required. But if someone wants something else, it's possible to create the initial way from the FloTHERM model. So you will be able to build a model for the application you are using. So FloTHERM is by Mentor. You can follow this link to read more about it. The next text here is from their homepage. Perform thermal analysis, create virtual models, and test design modification of electronic equipment before physical prototyping. We are using FloTHERM 11.1, and our modules is supported by 11.1 and the versions forward. There is another format for FloTHERM called XT, and we can provide those if you have request on it. We have done after request. So when you download our thermal models, our FloTHERM models, it's a zip file containing these two files. The PDML file is the FloTHERM model itself, and the PDF is a description of how to use our FloTHERM model. We'll go through the parts in this description briefly. The first section is 3D CAD geometry, which point out the point of origin. We have a domain of power loss distribution, which points out the different sources to power dissipation, and with tables that can be, at some parts there are different tables that can be used for different circumstances. But if your circumstances does not exist in this description, it is possible for us to provide additional tables if you have such a request. Next section is a domain of material and model calibration, where we state how our model is calibrated and under which circumstances. The last section is then the model usage, how to use the model. Final slide here is an example of one of our products, the 463, and how it looks when you do a thermal simulation in FloTHERM. You see the wind speed, and you see how the temperature in the different parts of the point of load 463.
Once again, I thank everybody for attending the webinar this morning. Thank you, Oscar, and thank you, Magnus, for the excellent presentation material. And we look forward to seeing you on our next webinar. Thank you very much, everyone.